Today we're going to talk about models. I'm going to start you off with a quote that statisticians really like. It's from George Box. It says, "All models are wrong, but some are useful." So in today's module, we're going to show you how models can be useful. So when we use the normal approximation in the previous modules with the talking about statistical inference, we were using a mathematical result, mathematical asymptotic result, to motivate the use of the normal approximation. Now when we use the t-distribution approximation, we did something slightly different. We made an assumption of heights, of the distribution of the population heights. We assumed they were normally distributed. That is a model. Now if you look at heights, if you look at the distribution of heights, they're very close to a normal distribution. We saw it in some of our previous modules. Here's an example of an outcome that is close to normal, but not exactly. It's baby weights. And in this case, we're showing a QQ plot, something we showed in one of our previous model in the exploratory data analysis module. It's very useful to check model assumptions. So we check if the theoretical quantiles of a normal match the sample quantiles of baby weights, and we see that it's close, but it does deviate a little bit in the tails. Now today we're going to give other examples where we use models and it's not always a normal distribution. So one example is the binomial distribution. It's another distribution that is not the normal distribution, and one way to think about the binomial distribution is it describes the distribution of the number of heads you get when you toss n coins. So in this formula, n is the number of coins you toss, and this formula gives you the probability of any number. So if you toss 10 coins and want to know the probability of seeing 5 heads, this formula tells you what that is. Now the binomial distribution is approximated by the normal distribution when n is large. This makes sense because if you take that sum of the number of heads and you divide by the total number of tosses, that's an average, and the central limit theorem tells us that averages converge to normal. But let's think of a example where this breaks down. Think about the number of people that win the lottery. Is that normally distributed? It should be if you use the central limit theorem without thinking too much. Why is that? Think about this. We have, let's say we have 10 million to 1 odds. That would be the probability of heads in the example of coins. We have 5 million people playing. The number of people that win is the sum of independent outcomes. You take the average, divide by the number of people playing. That's an average. Central limit theorem tells us it's supposed to be normal, but it's not. We've seen it, right? If we follow every time there's a lotto, most of the time nobody wins. Sometimes one person wins. And then there's the very strange examples where like 4 people win. So this is actually a histogram of those probabilities. And we see the probability of 0 people winning. Or this is the simulation where we actually ran a lotto 1,000 times. And we see that about 60% of the time, nobody wins. About 30% of the time, one person wins. This isn't normally distributed at all. So why isn't the central limit theorem working? This is one of the cases where the assumptions needed for the central limit theorem to work breaks down. It has to do with the fact that the probability is so small. And when you have this case, when you have the case where the probability is very small, but the number of cases, in this case, the number of people playing is very big, so big that if you multiply those two, you get a number roughly between 0 and 10. Then there's another distribution that helps here, and it's the Poisson distribution. So there's also a mathematical theory that tells us that when that's the case, when the number of coin tosses, if you will, multiplied by the probability of getting ahead is a number between 1 and 10, then the Poisson distribution describes this outcome. next modules, we're going to show how this Poisson distribution can be used in genomics.